Okay, great. Yeah, hi. So I'm Gareth Martin from the University of Hertfordshire. I'm going to talk about using cosmological simulations, large-scale cosmological simulations to make predictions for the low-surface brightness universe. Okay, so in terms of our understanding of how galaxies evolve, we're really limited by sort of current large surveys. So SDSS becomes incomplete at about 23 mags per square arc second in R. But sort of smaller, deeper surveys show us that there's a rich LSB population just below this limit. And so essentially the fact that we are unable to observe large numbers of statistical samples of these sorts of objects means we're biasing our understanding of the universe and of galaxy evolution. So one way of looking at this is to use large-scale cosmological lambda CDM simulations, and we can use these to predict properties about these faint populations. So the sort of current state of the art in terms of cosmological scale simulations are these fully hydrodynamical simulations like Horizon AGN, Eagle, Illustris, etc. And the one I'm talking about today is Horizon AGN. So it's a 140 megaparsec box, fairly high resolution, so a kiloparsec. So sort of caveat of that is we're looking at fairly massive examples of these sort of objects. And we have good agreement with observed morphologies, mass function, etc. So the sort of plan of this study is at redshift 0, we split our galaxies in the simulation into 3 groups. So high surface brightness galaxies, so they're objects that I can move now, can't I? So these are objects that lie on this side of the diagram. So this is surface brightness, and this is log number here. Classical LSPs, so galaxies that are just below the sort of high surface brightness limit here are in this sliver, and then ultra diffuse galaxies or ultra faint galaxies after that. So what we want to know is what are the properties of LSPs at redshift 0? How do these properties diverge from high surface brightness population? And then what's actually driving these divergences? So if you look at this, you can see clearly that low surface brightness galaxies account for most of the number density budget, but they account for obviously a fairly small proportion of the mass and luminosity budgets. So this table here sort of summarizes that, and the numbers of brackets are just what we get if we basically complete the surface brightness function here by extrapolating the mass function down to 10 to the 7 solar masses. So in terms of low surface brightness galaxies outside of cluster environments, so observationally, they're currently fairly poorly understood. So there aren't too many examples of these sorts of galaxies observed outside of clusters, so very few in groups of the field. And likely we're going to have to wait for wide and deep survey instruments like LSST in order to actually find significant sort of, samples of these. But this is something we can look at using simulations. So here I'm showing the distribution in stellar mass and average surface brightness in the R band in field environment, group environment, and cluster environments. And so you can see that even though the actual fraction of galaxies that are low surface brightness, so basically everything above this line, in clusters is obviously far larger than in groups or a field, what you have to remember is that only 10% of galaxies are actually in clusters. So in terms of actual aggregate numbers of objects, there's a huge population of galaxies that are low surface brightness in groups in the field. So in terms of the actual properties of these objects then, so I'm showing you here the distribution of a mass-matched sample of UDGs, LSBs, and HSB galaxies for various properties. So these are the effective radii of these galaxies. So obviously galaxies that are ultra diffuse have large radii. That sort of goes without saying. They also tend to have very old populations, stellar populations, although there's a fairly significant group of galaxies which are fairly young still. They have low densities of gas, so their star formation rates are generally quenched. But in terms of properties like dark matter fractions or halo spin, they're fairly typical halos for their mass. So in terms of the evolution of the effective radii and the gas fractions then, so here I'm showing you effective radius as a function of redshift for each of those same three populations I showed before. So after about redshift 1 for UDGs and classical LSBs, there's this fairly sharp upturn in terms of the effective radii, so this is about when things are falling into clusters. But if you look at the dashed line which shows field galaxies only, then they're actually evolving very similarly in terms of radius for UDGs. And there's a sort of fairly similar story for the gas fraction. So the shape isn't the same. So there's this drop in the star-forming gas fraction of galaxies, which you don't necessarily see in the field, but by redshift 0, they have very low gas fractions. So the main creation process of these objects doesn't seem to be cluster-specific. And we can show this in a different way. So this is the effective radius gas fraction plane evolving with time. So between redshift 3 and 2, these are essentially high surface brightness galaxies, and low surface brightness galaxies appear to be essentially homogeneous populations. And then UDGs begin to sort of pull away from the general population of high surface brightness galaxies. So the question is, why are they actually diverging? So part of the story is that the star formation histories of LSBs, and particularly UDGs, are much more bursty than high surface brightness galaxies. So they're essentially, so UDGs form most of their stellar mass before redshift 1, about 80%. And essentially, because you have quite rapid star formation, quite bursty star formation, this is going to lead to a large instantaneous injection of supernova energy. And essentially this leads to a shallower gas density profile. And if you have a shallower gas density profile, then this is going to produce a shallower stellar density profile. So this is the log-log density slope of the stellar density and the gas density, I believe, as it evolves. And I'll come back to this in a minute. But we can't, because of our resolution, we can't resolve the sort of dark matter effects. But so the other part of the story is the tidal field. So if we look at the perturbation index, so this is basically if a more massive galaxy comes closer to the object of interest, then the perturbation index is high. And you can see that if we look at the cumulative perturbation index, then for UDGs it's about 3 orders of magnitude higher than high surface for HSB galaxies. So in clusters, Rampress stripping is also going to help you remove gas. But clearly this, but galaxies in the field, so that's the dashed line here, they still have high perturbation indexes. So, so tidal perturbations seem to be the sort of main driver of LSB formation after redshift 1. But this formation is essentially triggered by the higher redshift flattening of the density profile by supernova feedback, which is going to reduce the binding energy. So in terms of future work, so basically we need higher resolution to study this triggering epoch where you have the supernova feedback. So this is a galaxy in horizon AGN. And this is the same galaxy matched in New Horizon, which is a 4 gigaparsec, so fairly large volume zoom of a region of horizon AGN with 35 kiloparsec resolution. And this means we can now resolve properly the processes that flatten the dark matter density slope, including the dark matter density. And we can also look at whether minor mergers might play some sort of role in this as well. So I don't think I have any time left. So I'll just summarize then. So low surface brightness galaxies dominate number density, not just in cluster spin all environments. So we need to understand these galaxies if we want to understand galaxy evolution properly. So their formation is triggered by supernova energy injection, which is due to fairly bursty star formation histories. This feedback leads to shallow density slopes in the stellar mass distribution, which makes them more susceptible to tidal processes. And then the tidal field can then expand the galaxies and remove star-forming gas. And one last note then, so the fact that these populations seem to be quite sensitive to supernova feedback, we can couple this with the fact that we have a cosmological volume. And then once we are able to compare this with something like LSST, this is going to be a way that we can essentially constrain supernova physics so that the subgrid recipes that we're using. The what, sorry?
The virial masses below objects, are they consistent with dwarfs?
Yes.
Okay.
Yeah, they're dwarf halos.
Okay. So what masses? I have the
So yeah, so sorry. So we basically
specify the mass ranges of halos where a large fraction of the numbers of right.
yeah, sorry.
So what is the mass range?
In terms of the dark matter halos,
For example?
in terms of the stellar masses, we're
No, the mass range of the halos.
I don't know. I'm not sure. I have to check.
You must have been looking at some mass range, not the very massive ones certainly do not form these diffuse or
No, they're dwarf halos.
But what does that mean? What's the mass range that you're talking about?
Like 10 to the 12, I guess. 10 to the 11.
It's a big difference.
Sorry.
If it's 10 to the 11, I understand what you're saying. If it's 10 to the 12, I don't. 10 to the 12 is the Milky Way mass.
Okay, sorry. Well, they're not Milky Way mass halos. Sorry.
Maybe it's the same question. So your three samples, so we saw
Yep.
a lot. Do they have the same mass or they have different masses?
They have the same stellar masses. They have the same stellar mass distribution. Yes, sorry. Around 10 to the 9. That's sort of where we're restricted to. Pardon? I'm sorry, I can't. Yep. Yeah, so I guess you can still have, there's still the tidal field in effect in the fields or groups, right? Because the interactions are essentially slower, so you have longer for the gravitational torques to affect, basically, I guess. But also the fraction of galaxies that are low surface brightness in the field is less, which you would expect.